Hey team, and welcome to the B-level lecture for 11.2 on atomic emission spectra. I want to make sure if you have not yet done the reading or watched the C-level video for 11.2, please take the time now to go back and watch that 11.2 C-level video or complete the C-level reading. I am going to reference that throughout this lecture, and this lecture also goes into math. The prerequisites for were both skills from 11.1 and the 11.2 C level. So our objectives for this lecture is now to perform all of the calculations for the atomic emission spectra that we just talked about. So we'll calculate the frequency or wavelength of a photon emitted from an atom, or we'll calculate an unknown energy level based on atomic emission. Furthermore, we're actually going to go past atomic emission spectra, and we're going to talk more about the properties of electrons. So up until now, we've been talking about electrons moving or transitioning up and down energy levels as particles, but it's also important to recognize that electrons, like photons, are quantum particles, which means they exhibit wave-particle duality. So we're going to look at some of those wave properties of electrons as well. So as a reminder, the way that atomic emission spectra are formed are when electrons make transition between energy levels in their atomic orbitals. The energy of the emitted photon is in fact just the difference between the energies of the two atomic orbitals that electron was transitioning between. We can relate this to what we know about the energy of a photon through Planck's equation. So we know the energy of a photon is h times f. Therefore, the difference between the two orbitals that an electron is transitioning between has to be equal to Planck's constant times the frequency of the photon that was either absorbed or released. And we're just going to talk about photons being released, but it is important to know that photons can be absorbed to cause these transitions as well. So let's say that we have this energy level diagram. It may look familiar. And we want to determine the wavelength of a photon emitted by that atom when an electron makes a transition from our third energetic level to our first energetic level. So first out, I'm just going to write what I know. The energy of my initial atomic orbital is negative 6.04 electron volts. My energy of my final sublevel is negative 54.4 electron volts. I'm looking for my wavelength, but I know that I have to solve for my frequency first because the only equation I know that deals with transitioning energetic levels involving photons is frequency. Next, I don't like electron volts. It's not my standard unit, so I'm going to go ahead, I'm going to convert those electron volts into joules. And again, I do that just by multiplying by the charge of an electron, which is 1.6 times 10 to the negative 19th. And this will give me my initial energy is negative 9.66 times 10 to the negative 19th. And my final is negative 8.704 times 10 to the negative 18th. I'm going to stop saying numbers from here on off because you can look at them and copy them down. Next, we are going to go ahead and look at the two equations we're going to be using. First, I'm going to calculate the frequency of my emitted photon using the equation we just introduced. And then I'm going to use my C equals frequency times wavelength to solve for the wavelength that was asked by the problem. From here, I just plug and chug. I do my initial energy level minus my final energy level. And again, because these are negative energies, it is very important to make sure that we are using our parentheses and remembering that a negative or subtracting a negative doesn't result in adding a positive. Planck's constant is 6.63 times 10 to the negative 34. I do my subtraction and I get 7.74 times 10 to the negative 18th. I divide by Planck's constant and I find my frequency is in fact 1.17 times 10 to the 16th hertz. From here, I can plug into my next equation to solve for my wavelength. And in doing so, I get 2.56 times 10 to the negative 8th meters. Go ahead, check that math, write it down if you'd like. I'm going to go ahead and move on, so pause the video if you want to finish writing stuff down now. Next, I want you to try a very similar problem, only this time we're working in reverse. So I'm now giving you the wavelength of the photon, and I want you to tell me what the energy of the n equals 4 level is. So pause the video, play it when you're ready to see the answer. Did you get that the energy of the 4th level was negative 5.31 electron volts? If so, congratulations, you are awesome. If not, you're still awesome, you just need a little bit more practice. So go back, rewatch the example, then resolve this problem until you know that you have got it. Moving on, you have now done all of the calculations involving atomic emission spectra. But now I want to talk about some of the nuances of electrons behaving as those quantum particles and exhibiting this wave-particle duality. So even though electrons, like photons, have energies like particles, and we can look at their charge like a single packet or a particle, when they move like waves. And in fact, just like with light, when you actually shine a beam of electrons or a current through a diffraction grating or slits like you would with waves, you actually see a diffraction pattern. So electrons, even though we consider them to be particles, behave like waves and can exhibit diffraction, which is really, really awesome. As a result, you can actually calculate what's called the wavelength of an electron. We call this the de Broglie wavelength. And it's really important because when you're talking about the energetic levels of an atom, the way that they started coming up with, all right, what does this energy level look like? How does this wave move? It started with the scientist named de Broglie and his wavelength. And so de Broglie figured out that the momentum of electrons is actually related to the wavelength exhibited by these electrons when they're actually moving. And so the momentum of your electron is actually equal to Planck's constant divided by your wavelength. So again, we see that Planck's constant. We're going to see it again and again throughout quantum physics. So let's see an example that's actually using the momentum of an electron and using this de Broglie wavelength. So say we have a photon emitted when an electron makes the transition from n equals 3 to n equals 1, and then it's incident upon a photoactive metal with a work function of 3.2 electron volts. So you'll notice I'm starting to combine concepts. This is not just 11.2 now, it's also 11.2 and 11.1. So I want to find the de Broglie wavelength of an ejected electron with the maximum kinetic energy. So this would be a two-step problem. If I looked at this on a test or a quiz, this would not just be find that de Broglie wavelength. I'd first ask you to find the frequency of the emitted photon. This is actually the same problem that we did in our first example, so I already can tell you the frequency of that photon is 1.17 times 10 to the 16th hertz. If you want a reminder of how I figured that out, please go back, watch the first example. And next, to find the de Broglie wavelength of our ejected electron, I first need to figure out what is the kinetic energy of that electron. Because if I'm finding the momentum to find that de Broglie wavelength, I need to know its speed. So I have the mass of an electron. It's 9.1 times 10 to the negative 31 kilograms. No, you don't need to memorize that. Yes, please write it down, but it is a constant. It will always be given to you. You just need to remember to look for it when you have problems like this. All right, enough of me talking. Let's get on to actually solving. So here are all of my knowns and unknowns, and there's a lot of them. My frequency is 1.17 times 10 to the 16th hertz. I just solved for that. My work function is 3.2 electron volts, but again, I convert to joules. My kinetic energy is unknown, but again, I'm looking for that because I need to know the speed if I'm going to calculate my momentum. The mass of an electron, again, it's a constant. It'll always be on your reference tables. It's 9.1 times 10 to the negative 31st kilograms. And then I'm looking for, again, my speed of that electron, and it's ultimately the de Broglie wavelength. I'm going to be using not one, not two, but three equations in this problem. First, I'm going to figure out what is the kinetic energy of my emitted electron. I'm going to use that using Einstein's equation from 11.1 on the photoelectric effect. Next, I'm going to solve for the speed of that electron using my equation for kinetic energy. And lastly, I'm going to use my new de Broglie equation to solve for my de Broglie wavelength. Here is that problem entirely solved out. So I took those three equations and I just plugged and chugged. I'm not going to go through all of the math. You can look at the math on the screen, you can follow the algebra, or you can text and call if you have questions about it, or think you find an error, which is also possible. But ultimately, understanding that we want to find the kinetic energy, to find the speed, to find the momentum, to find the de Broglie wavelength, that's really what you need to understand. Ultimately, you should find that your de Broglie wavelength is 1.82 times 10 to the negative 10th meters. But again, please go through, make sure this math makes sense, but make sure the process makes sense, most importantly. Next, I want you to take the time now to solve a problem on your own. Pause the video, read the problem, and play the video again when you're ready to hear the answer. Did you find that the frequency was 1.2 times 10 to the 15th hertz? If you did, congratulations, you are awesome. And I say that you are awesome because this is, again, a problem involving not one, not two, but three equations. And furthermore, I took this problem directly, word for word, off of an AP Physics B exam. Congratulations, you are doing college level physics. If this is still confusing, as always, please flip back to the last example. Go through it again. If you have any questions, text, call, or email, you know the drill. Otherwise, I'll be around to help you out with problems tomorrow in class. We've just covered all of our objectives for 11.2. We've done all of the calculations regarding atomic emission spectra, as well as examined some of the wave properties of electrons. I introduced to you the concept of de Broglie wavelength and how to calculate that, and we also applied this to 11.1, the photoelectric effect. I hope this blew your mind. It's absolutely awesome. Furthermore, this is also how something called neon lights work. It's also how we can get solar panels to work, specifically the photoelectric effect, but then getting these electrons re-excited to emit photons when we want to fluoresce something. So any fluorescence, highlighters, anything. It's awesome. So again, I hope this blows your mind, and I hope that you are invigorated and ready to go on and try the practice problems. Have a good night.